see my slides being shared, right?
Yes, it is visible, at least to me.
Perfectly all right. I would like to keep my video on. Okay, so without video on, maja nahi aa raha hai, right? So you do not see who is speaking and all that. So let me start my last lecture, but I would say it is not the fourth lecture, it is fourth and fifth lecture. As I told, I may take little more time. Perfectly all right, and hope you will give me time for that. Okay, so essentially these references and other things I have talked about. My disclaimer also I have talked about, because since it is a school, it is not my publication. So most of the stuffs are taken from existing literature, because without literature you cannot do science. Okay. So now after covering whatever is related so far, and with a good introduction of 4 vectors, and calculating center of mass energy from choosing a particle rest frame and all that. So I believe that most of you, even if you have not gone through particle physics as your specialization in your masters, again, I am not sure if you have done a little bit of 4 vector algebra recently, but I urge that you should do that. So assuming few things that you are accustomed with by now, let me go to estimation of threshold energy. And I can strongly demand, if you follow the recipe I am going to put up, irrespective of your specialization in MSc, you can solve any kinematic problems. And I have tried to do it as simply as possible. And I have also a couple of examples so that you are not lost. Okay. So in high energy heavy ion collisions particularly, or in PP collisions as well, so we deal with multi-particle final state. For example, although it is shown in a way it is a fixed target collision, so you believe that this blue and red, so they are colliding, because mostly LHC and star at a RIC, these are colliders. So let's see that these two objects are colliding, and I have multitude of particles produced in the final state, because it's a multi-particle final state scenario. So I consider projectile A, and with mass ma, energy in the laboratory as E lab. This collides with a target B of mass mb. Okay. So when I say it collides with a target of mass mb, the mb is at rest, and somewhere I could not put an arrow, but bold is also your 3 vector. So assume that it is a 3 vector. So pb is equal to 0. So your Newtonian momentum of the particle is 0. So essentially this gentleman is sitting, and this red is coming and colliding with it. So now the problem in hand is, so there are n number of final state particles produced, and let them be denoted by C1, C2, C3 up to Cn, and I designate them as different masses, MC1, MC2 and all that. Okay. So this is a multi-particle final state problem. A plus B going to C1 up to Cn. I do not know how many number of particles are produced, and my aim is to develop a formula which is a generalized formula for any number of particles in the final state, given that it is a 2 particle either fixed target or it is a collider problem. But for the simplicity, I have taken a fixed target kind of scenario. So that is the reason your PB is equal to 0. Fine. So now my aim is to define what is the threshold energy of the interaction and calculate or give a recipe using 4 vectors, which is simpler than individually demanding energy and momentum conservation in a non-relativistic way, or the traditional or conventional way. So I will give you a recipe. So then you should be in a position to calculate that. Okay. So before I proceed, can I define what is my threshold energy of any interaction? Yes. So this is the energy required to produce the final state particles. And I say it is any number. So you may say it is A plus B going to C plus D. Somebody may say, okay, let's generalize it for n particles, which I have done. And the threshold energy is defined that the particles are just produced, meaning their existence is denoted by their respective masses with kinetic energy 0. That means they are just produced without any velocity. Okay, so that is the definition of threshold production of the particles. Okay, they are just produced. Fine. So what is the recipe? So this is same for any kinematic problem. That is why I urge you that pay attention to, even if a newcomer without particle physics specialization should do it. Okay, that is my aim. So at least if 10-20% of you succeed doing in a 4-vector way, so I will be personally happy when I meet you in next collaboration meeting or in next school. So first step is write down the 4 momenta of the reactants and the products separately. Okay, so the way you are writing A plus B going to C plus D and all that, so you write individually 4 momenta of all that those are involved in the interaction. Then estimate the 4 momenta before and after the collision. Okay, suitably choose the frame of reference for the convenience of your calculation. So you have to see the before collision or after collision, which way I should choose my frame of reference, namely center mass frame or laboratory frame, so that my calculation is easier. Why I am saying it is as per your convenience? Because the next step is apply Lorentz invariant property of the scalar product of the 4 momenta. So once 4 momenta, the scalar product is applied, it is Lorentz invariant. So I do not care about your frame of reference because it is the Lorentz invariant. So that is why you choose your reference frame in a way so that is convenient for your calculation. Then what is the next step? You are done. Just to do some algebra and you are done. So let me take an example of this. So let me now derive the general formula for estimation of threshold energy. Okay. So as I told you, my first step is again write down the 4 momenta. So 4 momenta of particle A is EA and PA. So you should put an arrow, but my bold is, as per some books conventions, that is also my special component of the 4 vector. So now particle B, as I told you, is at rest. So this is at rest, right? And if it is at rest, your energy formula E is equal to, or E square is equal to P square plus M square will give me with the momentum 0. So this total energy is nothing but the inertial energy or energy because of its rest mass, which is mv. Fine. So now 4 momenta of particles A and B are written. So that is what you are going to do for any kind of interactions. So for the final state particles, as their kinetic energy is 0 by definition of the threshold energy, so the 4 momenta now can be written as they are just produced. So they are having their rest masses or the inertial energy. So then the total energy available is essentially sum of their masses. Again, by definition of threshold energy, your spatial component of the momentum is 0. If anybody is facing any problem in perceiving what I'm saying, you can just unmute and stop me to repeat the discussion. So now the step 2 is estimate the total 4 momenta, okay, reactants and the products. So in the laboratory frame I have chosen for before collision. You may see why I have taken laboratory frame. So now the P total mu I am writing for 4 momenta. So I add spatial components and temporal components. Temporal component is this one, energy part, and the spatial component separately. So now you look at here. So my temporal component is EA plus EB, giving me the total energy component, and on the right hand side it is PA plus 0 is PA. Okay, this is what's happening in the laboratory frame in the before the collision. Fine. So I choose after the collision as center mass frame, and usually it doesn't matter, okay, because these are produced in a threshold way so that their momentum is also 0. So P total prime I am writing after the collision. So now this is total energy is their rest mass energy. This is sum over MCIs, and this is 0. Total momentum is 0. Okay. So now I could write the total 4 momenta before the collision, after the collision, and before the collision I have chosen laboratory frame, after the collision I have chosen central mass frame. You can do also the other way. So now you apply the Lorentz invariant property of the 4 vector scalar product, so that my p square total, which should be p mu, one contravariant, another covariant. So that will give me p square total. So after and before the collision is Lorentz invariant. So you can write that p mu contravariant total, p mu covariant total before the collision is equal to the same quantity after the collision. Okay, but this is what we know, it is Lorentz invariant. So Lorentz invariant means it is independent of the frame of reference you have chosen. Fine. So with this, so you simplify the algebra, and this recipe is clearly given in our upcoming book with this example, example also. So you will find that when you simplify this 4 vector scalar product, so what you have to do is, so you multiply your temporal component, which will give you EA plus MB square, and minus sign will come from contravariant covariant. You remember, I remind you for that metric. So that takes care of the negative sign. So then you had PA square. So this is equal to your all mass. So I have written the capital M is my summation of all the masses. So MC square. And the momentum of the final state was 0 because it is a threshold production. So then once you solve it, do little bit of algebra, so you will get my EA is equal to MC square minus MA square minus MB square by 2 MB. So now I identify my EA was the laboratory energy, because one was fixed target, another was coming and colliding. I remind you that you recall the Bevatron antiproton production. One proton was static, another proton was coming with 6 GeV energy. So that was colliding with this, and you are looking into the production of antiproton P bar. Okay, conserving your baryon number, it was producing PP plus P bar. Okay, and we could see that once you go on increasing the energy, just after the lab energy was increased beyond 6 GeV, so antiproton production started in the Bevatron Lawrence Berkeley laboratory or California radiation lab at that time. Okay, the way it was known. So now EA is nothing but my lab energy or the projectile energy. So this could be written as MC. Now I write explicitly that MC is sum over the final state particle masses. So this square, okay. So you have to be very careful. It is not individual mass square, it is the total mass square. Okay, initially I did a mistake in the book. So then I corrected. So minus MA square minus MB square divided by 2MB. So this is the master formula to calculate threshold energy of any interaction. Okay. So anybody has any doubt on this recipe before I go to taking up one example? Just unmute and start speaking. You don't need any permission.
No, sir, it is clear.
Okay, thank you. So then let me take one example, because without example, nothing is clear. It is just mathematical prescription only. Okay. Okay, so I have taken one example which I verified later on with Anki, because Anki works in Wajakoji. So this example, if you see in Wajakoji experiment in Jülich, Germany, proton beam is used on a fixed target to produce eta prime mesons. So now I am asking you that estimate the threshold energy required for the formation of eta prime, and the reaction mathematically. You see, always while solving a problem, you should translate this statement to mathematical formulae. So now your PP, one P is stationary, another P is coming and colliding. You are producing PP and eta prime. Okay, so this is the interaction. So now let's write down the masses, because I need to use this formula. Okay, so the masses of the particles are the following. Your proton involved in the interaction has mass, exactly I have taken this. Eta prime mass is 957. I used my previous equation, which is this one, to calculate the eta prime production. So my aim is to find out what is my E threshold in the laboratory. So after I write the master formula, I identify that my particles in the final state are 2 protons and 1 eta prime meson. So 2 proton is 2 MP plus eta prime meson. So this whole square minus, so MA and MB are my 2 protons here, one stationary and another called projectile. So this is 2 MP square. I plug in the value of MP and M eta prime, and finally I get 3.34 GeV is my threshold energy for the production of eta prime mesons. And that is what I verified with Anki, that their threshold energy in that experiment is also 3.34 GeV. Okay. So I made a theoretical calculation. I confronted to the experiment. It is correct that if my laboratory energy is 3.34 GeV, so I could produce eta prime mesons in the Waja-Koji experiment. Perfectly fine. So I tried to draw some physical meaning out of this energy. So since I am working in LHC, so I extended the discussion in this book to little more to draw different inference. For example, if my lab energy is 3.34 and my LHC works at much higher energy, so let's try to draw some conclusion from the speed, beta, and all that. So I went on calculating gamma factor, which is E over M, and given the energy is now, I am taking this value. Okay, you can take this one also. So, so when I divide my mass, I am getting 3.62 is the gamma factor for Waja-Koji. Okay, if I solve for the velocity is coming like your beta is 95.978%. Okay, so now I wanted to see if I go to LHC. So if I go to LHC, your beam energy is in order of TeV. So I exactly went up to 3.5 TeV, which is almost 1,000 times higher. So energy is now 1,000 times higher. So if I calculate the Lorentz factor exactly following the same prescription, I found that your Lorentz factor is almost 1,000 times. Okay, so Lorentz factor is almost 1,000 times, because you will find when I talk about, I have a dedicated slide for Lorentz factor. So it is nothing but your energy at the end, right? Because MP can be taken as 1 GeV. So in the unit of GeV, whatever beam energy is, so that is your Lorentz factor. It's very easy to know. So now if you see, compare Ulick with Chern, so you will find 1,000 times higher energy gives me 1,000 times higher Lorentz factor, right? Almost if you compare this number with this number. What about the velocity? So velocity has not changed. You see, your beta was 95.97%. Now it is 99.999%. So velocity changes very tiny amount, whereas your energy changes almost 1,000 times. Are you learning something beautiful from this? Okay, so it is a practical example of making a journey from Waja-Koji to Chern, and you find that your velocity is not changing. And again, this confronts to why LHC has different rings of different diameter or periphery, while feeding the beam to the LHC, why sequential acceleration is necessary. Okay, and it also mathematically convinces me that if I go to higher and higher energies, my relativistic mass becomes higher and higher, so that the velocity is almost saturating, and you will find a asymptotic value. And my question of yesterday, if you go to FCC, the future circular collider, you cannot reach the speed of light. It will just modify in the 10th decimal places or 12th decimal places here. Okay, so you cannot reach speed of light. So that is the beauty of this mathematics, and we also realize the same thing. And it has technological consequences, which I am not discussing now. Okay. So another example, actually, I have also tried to take from KEKB factory, where B mesons are produced copiously, okay, to study the CP violation process. And they also take exactly, since final state you have only epsilon 4s, okay. So epsilon 4s energy will be the threshold energy, and that is what I will show you in the conversion of center of mass energy to lab energy and vice versa. So you will find the asymmetric E plus E minus collider, the way they have chosen the energy of E plus and E minus, exactly the center of mass energy available for epsilon 4s production is 10.58 GeV, which is nothing but the mass of epsilon. Okay, so this threshold energy actually helps us in determining what should be the beam energy to produce a particular final state particle. Okay, so this concept is also used in various accelerators, but I have taken this example from KEKB factor. Okay, so now let me migrate. If everybody is content and now you know how to apply 4 vectors to calculate threshold energy of any interaction. So now let me slowly migrate to collider versus fixed target experiment. So why collider experiment and why fixed target experiment? There are specific objectives. So as you know, we look into the debris after the collision. So the debris is essentially the produced particles in the system. So if you know that fixed target experiment, so my target is fixed, my projectile is coming and colliding. So this damage, the severity is much less compared to a highway head-on-head collision where the damage is higher, right? And I, as a heavy ion physicist, so I look into higher damage, right? So higher damage will give me the proper debris, and I can look into or characterize the debris to conclude about the formation of quark-gluon plasma. So mathematically, so although I could show you philosophically this is more favorable to study quark-gluon plasma, there are also different advantages of studying fixed target experiment. Maybe you may look into Subhashish Das's evening lecture or so he may talk about CBM. So advantages of fixed target experiment, we will know that. I don't want to digress from my discussion. So now the energy available for particle production in the laboratory, which is the fixed target experiment shown here, will be the square root of E beam. Okay, and if you go to center mass frame, which is a collider like this, so energy available for particle production goes like E beam, 2 into E beam. Okay, so this is square root and this is without square root, meaning more energy is available in the center mass frame. Okay, and if you look at the fixed target of 440 GeV, if you go for a similar beam collision with collider mode, you will have energy available almost 900 GeV. So energy available here is 29 GeV and this is 900 GeV with the same beam energy. Okay, so that is one of the reasons that colliders are more preferred. Fine. And just to give a couple of examples, the people working in STAR experiment, they must be knowing this, and our LHC people must be knowing this, and these are colliders. And the next generation experiments like NICA or FAIR, so these are actually upcoming experiments which will be fixed target for a particular physics M. Okay, so which I'm not discussing because that will be digression. So now let's derive the formula for collider versus fixed target experiments, because you may need those formulae to use when you plot some observable as a function of center mass energy. Because in fixed target experiment, so they talk about beam energy, and in the modern experiments like STAR and ALICE, so you talk about center mass energy. So this conversion formula will be important. And what I am going to do is I apply the same 4 momentum concept to get this conversion formula. So now let's consider the 2 particles in laboratory frame, projectile of momentum P1, energy E1, and mass M1 that collides with the target particle of mass M2, which is at rest. So the 4 momenta of the particles can be written, which is the first step in my recipe. So P1 is E1 P1 and a P2 is M2 and the momentum is 0. So in the center mass frame, your P star 1, okay, so I'm writing star for the center mass system. So in the center mass frame, your P1 star is equal to E1 star P1 and P2 star will be just this one will be negative of P1 because total momentum in the center of mass frame should be 0. Okay, so the square of the pore moment of the system is conserved quantity, as you know. So then I apply in the center of mass frame, my P1 plus P2 square is nothing but spatial component square minus temporal component square. And since in center of mass, this total momentum is equal to 0, so this gives me E1 plus E2 square. And E1 plus E2 square, I write E center of mass because that is the total energy available in the center of mass frame. And it will be shown, or you also know from Mandelstam variables, which I introduced last time. Actually, somebody's mic is unmuted. Can you mute it, because that is creating some background noise. So in my last class, I showed you Mandelstam S is nothing but P1 plus P2 square, right? So if I write ECM square is S, essentially your square root of S will be ECM. So E energy available in the center of mass is equal to the square root of the Mandelstam variable. So few people I have seen while writing, they make capital S. So remember that your S has to be small in order to designate the Mandelstam variable, which is P1 plus P2 square. S has to be small. So keep in mind. So this S prime is the total energy in the center of mass, which is invariant mass of the center of mass of the system. And in the laboratory system, P1 plus P2 square could be shown to be M1 square, M2 square plus 2E1 and M2. So you know this because individually, if you expand this will be P1 square is M1 square, P2 square is M2 square. I showed you earlier. Then you will have the term like 2 into P1, P2. P1, P2 can be expanded into spatial component, temporal component minus the spatial component. In the minus part of the spatial component, you will find P2 is equal to 0. So then once P2 is equal to 0, the energy of the second particle is M2 and energy of the first particle is E1. So that in laboratory system, this same quantity is nothing but M1 square plus M2 square plus 2E1 M2. So now, since it is invariant, so this can be equalized with this one. So E center of mass square is equal to M1 square, M2 square, and 2E1 M2. And I will be writing my E1 as the projectile energy in the laboratory frame. Okay, so this is the way I equalize these two and use that formula for conversion of fixed target to collider energy. So you will find this expression. That is what I told you. So given that you have E projectile in the fixed target or energy available, energy of the beam in the fixed target, you can actually convert that to the center of mass energy E center of mass using this formula. Okay. So this formula you will be using for many purposes. So keep in mind. And gamma center mass I have already talked about. So that is the total energy available in the laboratory, which is E1 plus M2 divided by it should be a mass, and this mass is essentially your square root of S behaves like a mass, invariant mass of the system. Okay, so this formula will be used here and there, so you have to keep in mind. And in the master formula, so if I take a collider head on where the theta is equal to 0, essentially you can calculate taking theta 180, this will be positive. Okay, in principle it should be negative because I have observed cos 180 degree minus sign here. Okay, so for relativistic collisions, I know that M1 and M2 can be ignored in comparison to the total energy E1 and E2. So in that case, your E center of mass square can be written as 4E1 E2. So if you have a symmetric collision with same energy E1 and E2, so you'll find I can write E1 is equal to E2 as E. So then if I take the square root, so this will be 2E. So 2E will be my energy available in the center of mass. Okay, so that is what I talked about. E center of mass will be 2E for a symmetric collider. And if you calculate for the fixed target experiment, so this will be 2E1 root over. So that means more energy is available for particle production in a collider in comparison to the fixed target experiments. That is what I showed in that slide where I just use the formula where I showed the cartoons. Okay, so so highest energy available for new particle production is achieved in the collider experiments. And if you calculate the SPS fixed target experiment to achieve a center mass energy of 17.3 AGV, this AGV, how it is coming, so I will show you in one of my slides. And the beam energy will be 150 AGV. Okay, so in the laboratory, you need more energy of the beam in comparison to center mass energy. So the converted value is 17.3 AGV. Okay. Yeah. So there are a couple of notes for the newcomers. More often, collision energy is expressed in terms of nucleon center of mass. Instead of writing S root over S, we also write S with a subscript NN like this. Okay. So meaning is it is per-nucleon center of mass energy. So how it is related to Mandelstam S, which is the center of mass energy in total. So that is, you have to multiply the mass number A. So square root of S is equal to A square root of SNN, which is per-nucleon center of mass energy. Okay, this is what in any of the papers you will find the energy we write for heavy ion square root of SNN. And earlier papers, if you see SPS literature, so you will find the beam energy is written like 158 AGV. So if you are using lead, so then you have to multiply the mass number of lead. So that is also another way of using per-nucleon. Okay, so a little bit of homework for the beginners. So since you have started using root and root-based C++ programs, now you write a formula, you know from here, just to do a simple coding to convert the laboratory energy to center of mass energy for any A plus B type of collision. Okay, any sort of like proton with a lead kind of collision, it should be able to calculate. And why I'm saying is, you will find, once you do it, you will find the problems. Okay, and to standardize your program as a QA check, you should take 150 AGV and beam energy in the laboratory, and you should see that your center of mass energy should be 17.3 GV. So that will actually make a QA for your code. So if that is working fine, so then possibly other conversions will be okay. And this will be very much useful when you plot the excitation function or anything as a function of square root of S, because you have to take low energy data and high energy data, and low energy data will be available in the fixed target mode. Okay, so that is why this program will be quite useful. And for the advanced learners, whoever are in the higher stage in PhD, so write a Monte Carlo program in root to use three-dimensional Lorentz boosting for the invariant mass reconstruction of rho going to E plus E minus. So in the Monte Carlo program, you can assume your energy spectra, or you draw at mid rapidity from a rapidity exponential rapidity spectra or flat rapidity spectra. You try to have your energy and then decay rho to E plus E minus, and it should be a three-dimensional decay. Then do the Lorentz boosting and have your invariant mass reconstruction and try to see if you are getting exactly where you expect. Okay, and in addition, you can also use 10% detector resolution and see how detector resolution is changing your delta peak to a Gaussian peak. Okay, this is what I did under the instructorship of Professor Basant Nandi in one of the ACRC schools in DCC Calcutta a long time back during my PhD time. So I urge you, the advanced learners, have fun with this. Okay, and if you face, I am keeping that program till now as a pride. Okay, couple of students we could do it. So if you can do it, so let me know. Okay. Okay, and you can also check, in my program. So I try to check all these things, your P beam versus what you are getting as the center of mass energy, the conversion. Okay, and you can try and check your code if you are getting the values properly. Okay. Yeah, I think I can skip these things, because once you do this these analysis, you can calculate all what you need, like your y projectile, which will be minus of y target in a collider mode, okay, and this will be equivalent to your y beam, and this can be written as logarithmic of square root of SNN by MP. Okay, so these things you know. So I will try to skip those things, and now taking the exact values, the one I specified in one of my last slides, in KEKB asymmetric collider in Japan. So in order to produce this copious B mesons, so what they do is they take E minus with an energy of 8 GeV, E plus has 3.5 GeV, okay, and in the collision they make an angle of 11 milliradian. So why 11 milliradian? So that is a question to all the experimentalists you can think of. Instead of making a head-on collision like this 180 degree, why they take 11 milliradian? Okay, so that if anybody can answer, that is fine, or I have written already. I have written the answer, so fine. Somebody might have read it. Forget it then. So, so given the beam energy E1 as 8 GeV and E2 as 3.5 GeV, the angle is given. So you convert this milliradian to degree and then use the formula E center mass square is equal to 2 into E1 E2. Mass can be ignored because the electron mass is 0.5 MeV. So it is very small mass. So you put all these values and then you will find E center mass is equal to 10.58 GeV, and this is nothing but the threshold production of epsilon 4s. Okay, so can anybody tell me if in this process why they are taking the angle of the collision 11 milliradian? Although I have written in last slide and I specified, somebody might have seen it already. Huh? Think and somebody should try to answer. Just give me a few seconds break. I'm just coming. Yeah, so why the cone is not head on the way we make it in, let's see why they make it plus minus 11 milliradian. Any answer? That is almost a non-kinematic problem, but kinematics is also involved to decide that. No? No answer? Just give a wrong answer. What is wrong in giving a wrong answer? Try to give a wrong answer. So let somebody speak and give a wrong answer. And I will see what will go wrong. There is no bomb to blast if you give a wrong answer, right? I should not take name of the student. So then, it may be a little embarrassing for the student sometimes. Yes. So if I have to take a student name, so I have to take maybe my own student so that he cannot react, right? Dusmat, are you there? This is
Yes,
somebody
sir.
left.
Yes, sir.
Okay, so then the reaction level will be less. So can you think of why KEKB factory has 11 plus minus 11 milliradian collision? Like, it is happening in this way. If you can see my
Yes, sir.
fingers, okay?
Yeah, so
LSC is like this.
right.
So why? What
So
the
one
just
reason maybe that.
think of abruptly out of the box which may go wrong, and I will see what kind of bomb is going to explode.
Yes, sir. So one reason maybe that in like a head-to-head collision such as LSC, so we place detector which are almost like 4 pi like kind of detector. So
Yeah.
that may take actually, it will be actually really costly to build such kind of detector. But if the reaction is happening with a small theta, so then the detector will be placed at the front only. So it will be cost effective.
Yeah, it is exactly with the, their physics aim is very fixed, unlike our LHC detectors, which are with diverse physics aims. So since they are looking into CP violation in B sector, they have put all their detectors in the forward cone only. So once, it is a kind of fixed target, but not fixed target. Okay. So they make the collision like this. They achieve the threshold energy to produce beam agents copiously, and they put their trackers and everything in the forward direction. That also reduces their cost. Okay. The particles are produced in the forward cone only. Okay. And in LHC, when you have this kind of collision, head-on collision, so there is symmetric emission of particles in all directions. So that is essentially the reason. So they take forward cone 11 milliradian collision. Okay. So kinematics actually helps in discussing about this kind of considerations. So yeah, again, little hindrance. Somebody is knocking our. Yeah, I'm sorry. Actually, there was someone on the door. Okay, so now let's see the next problem. These problems actually are frequently asked by many people, right? For example, given the PP maximum beam energy, how to estimate the achievable energy for heavy ion collisions? For example, if you consider the beam energies at LHC for PP collisions, so what are the energies one can achieve for heavy ion and lead-lead, xenon-xenon, oxygen-oxygen, and p oxygen or p lead kind of collisions? Is it abrupt? If you see the table, whatever LHC has taken data at different energies, you will find that sometimes it is 5.02 for lead-lead, 5.44 for xenon-xenon. So now the question is it abrupt that it is coming, or there is a fast-hand calculation that if your energy is achievable for PP collision is 2.76, 900 GeV or 13 GeV TV, so then your corresponding PA or AA collision energy will be whatever I told you initially. Okay. So the answer is, depending upon your accelerator system, if achievable energy for proton beam is something, so then you can calculate what will be your energy for heavy ions. Okay. So let me give that prescription, because some of you must be using the given value from whatever data are available, but without thinking little more if it is calculable or it is abruptly LHC is delivering you the energy for heavy ions. So to answer this question, so let me proceed. So an accelerator is capable of accelerating protons up to a certain beam energy of EP. Okay, let me write that EP is the proton beam energy. So what will be the maximum center mass energy for PA and AA collisions? So to answer this, you see, I have written so many things. So just follow me and then it will be very clear. So in heavy ion collisions, the atom is fully stripped off. with electrons, right? So sequentially, what happens is sequentially we go on stripping up the electrons so that a higher charge state is available for acceleration. And you know, higher charge state will help you in easier acceleration. Maybe you can try to see in our accelerator class tomorrow or day after. So the nucleus has Z number of protons and N number of neutrons, and I can say that it is A minus Z is the number of neutrons. Neutral particles, you know, they cannot be accelerated independently, and here it is neutron. So the charge state of the nucleus is responsible for obtaining the required energy in the acceleration process, right? So this you know. Fully stripped means the charge state equals to the total number of protons inside the nucleus. So all electrons are stripped up. So this is the highest charge state for that particular ion. So what is left over then inside the nucleus? So you have protons and neutrons. And you know, neutrons being neutral particles, they are just free riders in the process of acceleration. Okay, you have to accelerate the charge state, which is number of protons, whereas neutrons are just sitting as free riders. So you have to spend time, energy for neutrons acceleration, right? So you need to spend energy for protons to accelerate the neutrons, which are free riders. So because of this, when you convert your pp energy to center mass energy of heavy ion collisions, it is just not the multiple of Z, okay, which is the proton number. It is essentially a reduced value because to spend energy for these neutrons, which are free riders. Okay, and there is a mathematical prescription which I am giving in my next slide, so you can calculate what will be the energy. So for head-on heavy ion collisions, so I could write my earlier formula as Nn root over per nucleon center of mass energy as 2 into E1 E2 root over. So for a collision of two different nuclei with charges or atomic number as Z1 and Z2, the atomic masses as A1 and A2. So now my E1 can be written as E proton multiplied by Z1 by A1, right? E2 can be written as E proton Z2 by A2 because I am just multiplying E proton with Z1 for heavy ion divided by A1 because A1 is taking care of Z1 plus N1, the neutrons and also the protons. Okay, so now using this formula, I can write this as 2 of E proton Z1 Z2 divided by A1 A2. So this 2 into E proton is nothing but my SPP, the center mass energy available for proton-proton collision, and it is essentially addition of the two proton energies, right? Because it is center mass energy, and although nobody writes SPP to designate that from SNN, so I have introduced SPP here. This is essentially your Mandelstam S, because per-nucleon is not applicable for proton-proton. So now this formula. So for symmetric collisions with atomic number and mass ZA, so if I have a gold on gold collision or lead on lead collision, so Z and A both are same, so then this root over can be taken out. So SNN per nucleon center mass energy for heavy ion collision is equivalent to your SPP, the proton-proton collision, and multiplied by a factor which is Z by A. Okay, it is just not Z multiplication, it is also division by A to take care of your masses. Okay, so this is the formula used. For example, if you have a proton energy available for a particular accelerator, what will be the energy available for heavy ion collision is decided by this simple formula. Okay, and you will realize I have given a table here till the data taken up to 2018 for PP collisions. So whatever energy is available, I have written here. So LHC has accelerated protons with 0.9, 2.36 up to 13 TeV. Okay, and if you calculate using that formula, what could be the lead-lead center mass energy or xenon-xenon center mass energy, the corresponding energies are given in this table, and you will find exactly the lead-lead data or xenon data 5.44. The star marks are actually the data taken by LHC. So you will find when PP center of mass energy is 7 TeV, for example, 3.5 is the beam energy. you will find the heavy ion collision happens at 2.76, and for which we have the data. Okay, so I think this should convince you migrating from PP, center of mass energy, to what is achievable in that particular accelerator for heavy ion collisions. Okay, so the general formula is this, and for symmetric collision, actually you can write SVP root over by ZA. So if it is not symmetric collision, for example, you want to explore what is my P-led collision energy. So P-led collision, you have to use this formula particularly, and you will find that these energies are actually available. 5.02 TeV, 8.16 TeV for P-led collisions are available. Okay, so any question on up to this slide? Okay, so if not, so let me quickly go to Lorentz factor. Lorentz factor almost I discussed while introducing Lorentz factor, taking energy and mass, essentially in the given situation where we can distinguish per-nucleon center mass energy versus the Mandelstam S center mass energy. So we can actually rewrite and do a little bit of algebra to write in our own language. So I start with the example of E by M, and then slowly I write the energy is square root of S, and my mass is nothing but 2A MP, which is for heavy ion collisions, heavy ion head-on collisions. Now you will find that this A square root of S can be written as A square root of S NN. So nuclear number multiplied by per-nucleon. So that is the total energy Mandelstam. So square root of S is equal to A multiplied by square root of S NN. So A will cancel out, and the end you get square root of S NN divided by 2 MP. And for a center of mass system, your beam energy is nothing but square root of S NN by 2. So if I put that, so I will find that gamma factor is nothing but E center of mass beam energy divided by MP. And since all will be in the same units, for example, if I am using my GV unit, so MP is like 1 GV, and your gamma, just to have a physical feeling, is nothing but the beam energy in the center of mass. So if somebody will ask you what is the Lorentz factor or gamma factor for PP 13 TeV collisions, so immediately you should answer your center of mass beam energy for 13 TeV is 7 TeV. So 7 TeV is 7000 GeV. So 7000 GeV is your 7000 is the gamma factor for PP collision at 13 TeV. Okay, so I have given this simplified formula so that it is easy for you to answer what is the Lorentz factor for a particular collision or particular energy. So this is just a plot to show. Thanks to Pragati actually helping me to draw this plot in root. Okay, so the Lorentz factor goes on increasing, Okay, so now let me get back to rapidity. Essentially what I am going to discuss is available in the book of Wong, and more elaborately available in our books with Professor Nandi, so it is not yet public, but still. Let's go to rapidity in a detailed discussion mode. So the particle 3 momentum can be decomposed into longitudinal and transports, and PZ and PT, these are the things we use in our experiment, right? And the PZ is longitudinal, Z axis is chosen to be the beam axis, and transverse is PT. All transverse components are actually very good, at least for all of us, that there is no Lorentz transformation, because that is invariant under Lorentz transformation. That is the reason all PT, ET, this kind of things we are habituated, or we like to use them because of Lorentz invariance. And the rapidity earlier I defined as half log E plus PZ divided by E minus PZ, and you can also write in terms of MT. MT is your transverse mass. You may be knowing that is M0 square plus PT square root over its transverse mass. Okay, it's a new concept because the newcomers may start thinking, what is transverse mass? It is a scalar, right? So I cannot decompose to longitudinal mass and transverse mass, but MT is defined for our use, taking PT into account, like M0 square plus PT square root over. Okay, And we can also show that rapidity changes by an additive constant, which I showed earlier. These are little bit of repetitions for the sake of complete discussion of rapidity. And this I showed you that your y rapidity of the particle is nothing but in the center of mass rapidity plus rapidity of the center of mass. Okay. And so you could see that in the center of mass frame, although the mid rapidity was at 0, when there is a Lorentz boost and I'm going to the laboratory system, so this is exactly shifted by y beam, which is 8.52. Okay, so the mid rapidity is now shifted. So these things I showed you earlier, and just these are important point to bring up is the shape invariance. Okay, so shape invariance helps us a lot in drawing physics inference from these plots. And the y beam can be shown to be y maximum, so that is the maximum rapidity. And in different event generators, when you look at y beam or y maximum, because you have to tune your x-axis, so you will find you can actually calculate taking your center of mass energy on which you are working. So what when your one student is plotting the rapidity, so he or she does not know in the first go what should be the range of my x-axis, but I would urge that you first calculate by hand for a given energy what should be your y maximum. So then you choose your x-axis. Otherwise, what will happen is you will find some of data points are missing, then you extend your x-axis. That we have done during our early days of PhD. Okay, so that is a fun. So now to your known observables like E and PZ, which are not always measured because energy measurement is a different ball game, you might have known by now. So I should be in a position to change EPZ to Y and PT, okay, which are measurable in experiments, although Y should be changed to pseudo rapidity slowly. So I'm developing those formula. So you can see that if I have to change from the coordinate system of EPZ to YPZ, so I will write that E is equal to MT cos hyperbolic Y and PZ is MT sin hyperbolic Y, where my MT is defined as M square PT square, as I told you. Okay. So yeah, this formula actually I have given you earlier. So the rapidity of the center of mass in the laboratory frame, if I go on defining, so your Y center of mass will be just in the same formula you have to rewrite, because your E and PZ, so you know E and PZ, and your gamma or beta will be always gamma center of mass and beta center of mass. So from the original definition, you can write all these things. And after cancelling out, you will find your Y center of mass is nothing but half of log of 1 plus beta Cm divided by 1 minus beta Cm. So then this is a constant factor because beta Cm is a constant for a given energy. So now the relationship between rapidity of a particle in the laboratory system and the rapidity in the center of mass system will be very simple. Okay. So you convert the rapidity definition from here to your Y star, which is in the center of mass frame, and you will find that is very easy to do. And at the end of the calculation, using the conversion formula for E star to E, that means your Lorentz transformation, plugging in all these observable variables, you will find your Y is nothing but Y star plus Y center of mass. Okay. So this also, since Y star, Y center of mass is a constant quantity, essentially that gives little shift in the origin of the spectra, thereby making shape invariance. Okay, that is the beauty of introducing rapidity or using rapidity. Okay. Okay, so how am I doing with time? Yeah, so I think it is fine. So in other words, the rapidity of a particle in a moving or boosted frame is equal to the rapidity in its own rest frame minus the rapidity of the moving frames. That is what I showed you, and the most important thing was the shape invariance. And in a non-relativistic limit, so this is like the subtraction of velocity of the moving frame, right? Because you recall your Galilean relativity, you will find it is just exactly equivalent to the subtraction of velocity. Is it surprising? Answer is no. Because you can also show that the longitudinal velocity beta is the non-relativistic realization of rapidity Y. So you can show that, and there is a discussion on this in, I think, own book. It is also there. Okay, so you can show that. So now let me migrate to beam particle, beam rapidity. So what is the rapidity of the beam? So now we know the formula E is equal to mt cos hyperbolic y, pz is mt sin hyperbolic y, and mt square is m square plus pt square. These are the formula given to us. And for the beam particle, since it is traveling in the beam axis, the z axis, your pt is equal to 0. Okay. So if the pt is equal to 0, so you can rewrite this formula in the way that E is equal to mb, because it's a beam particle. Okay. And pt is equal to 0. So the rest mass of the beam particle is coming here, cos hyperbolic y beam. Okay. So similarly, your pz is written, and you can find out your y beam is cos hyperbolic inverse of E over mb, and finally the formula is this. And when you plot your beam rapidity as a function of square root of SNN, you will find this goes like this. Okay, and this has to be related with your gamma factor, because I showed you also earlier the plot of gamma factor. It was just increasing like this. Okay, this has to be related to the gamma factor. So you can show that your y beam is equal to y maximum, and that is related to your square root of Sn by mp, and this is nothing your gamma factor, if you say. Okay. So, and y beam is studied mostly while studying the physical phenomena like limiting fragmentation, but I think I may not discuss that because of time constraint today. I took out those slides yesterday. Fine. And mid rapidity in fixed target and colliders, this also you should know as a part of kinematics. And so in the laboratory system, your y lab is equal to y target plus y projectile, and this is equivalent to your y beam. And the mid rapidity in fixed target will be your y mid laboratory system is equal to y beam by 2. So that will be the mid rapidity. And in the collider system, your y projectile is equal to minus of y target, and this is equal to ycm, and this is again y beam by 2. But so then your mid y in the center of mass will be 0. So that is what you saw, that your rapidity spectra is peaking at 0 for center of mass system, whereas in the fixed target it was shifted to your y beam. This is valid for symmetric collision, and for asymmetric collision like PA, a rapidity shift has to be taken into account, which actually because of time constraints, again, I'm not discussing that. Okay, so but formula I'm giving, how to derive this formula I'm not discussing for this. And your delta y for PA kind of collision, the rapidity shift is half of log Z1A2 divided by Z2A1. So this I am not discussing. And then the maximum accessible rapidity, anyway, I made a discussion, and you can also derive that because your definition of y is half log E plus pz by E minus pz. So you can write the formula in terms of tan hyperbolic y, and your y maximum, if you take, so using this formula, you will get it is cos hyperbolic inverse of gamma, and if gamma is always greater than 1. So this typical plot you might have seen, which is a beautiful plot, and I remind you that YCM is always 0 for collider experiments. And if you look at with energy availability, from very low HGS energy to SPS, REAK, and LHC, so slowly your rapidity range or accessible rapidity is going on increasing, right? So people who migrated from REAK to LHC, so they also know that earlier our kinematic plotting range was very less, so now it is higher and higher because of this formula, higher gamma being available. Okay, Lorentz factor is higher, or the energy is also related to the Lorentz factor, which is higher. Okay. Okay, so you can also show that rapid differences are also Lorentz invariant. So this maximum accessible rapidity can be calculated, which is essentially equivalent to your YB, and you can see YB positive, YB negative. So that actually gives the total available rapidity. The rapidity is essentially minus YB to plus YB. And this minus is convention because as you know, the velocity positive or negative, like your coordinate system, is a convention. So positive rapidity versus negative rapidity, these are actually conventions, the way you take it. So Y maximum or Y beam is essentially logarithmic of square root of SNN divided by 2MP. So this is required for our kinematic problems. And while running any event generator for event simulation, you can actually check this formula if this gives the right result or no. So when you plot your dn by dy, you will find the maximum in the x-axis will be limited by this y max. Okay, so you can check this. And just for a physics plot, let me show you the pion spectra dn by dy spectra as a function of y. From very low energy to weak energy, if you see, the range is also x-axis range is increasing. Okay, so that also telling me that with higher and higher energies, your y maximum, which is equivalent to y beam, is also going on increasing, following this formula. And should I skip a couple of things on rapidity properties and conversion to pseudo rapidity and that mass dependent suppression at mid rapidity, so that I can save time and go to invariant yield, because we are almost touching 1 hour. Siddharth?
Maybe you can quickly tell, because there might be new students.
I realize I am going little faster, although covering whatever they need for their practical use. But going faster also, I do not like that somebody is lost or I am just switching from one slide to another slide.
Or maybe you can assign them as a assignment.
In fact, in most of the textbooks, these discussions are there. Okay, but I have elaborated it so that you know the missing points which you do not catch it immediately from Ong or Ramana books. So this discussion has more elaboration. Okay, so that is the advantage of what I have put it here. But mostly these are textbook matters, the rapidity properties and migrating from rapidity to pseudo rapidity and how that mass dependent dip is coming. So those things are essentially part of the textbook discussions. So
maybe Raghubai, I think that you may explain, because these are very, very important things at least.
Okay.
So, we'll see about the timing. Yeah.
Okay. So maybe I will borrow 10-15 minutes minimum from Saikat if Saikat is not complaining. Okay, so fine. Let me go a little quick, because anyway, you will find these things in the textbooks. And as Siddharth told, these are also important for the new students. So rapidity is a relativistic realization of the particle velocity. I may show taking one example later on. And it is a dimensionless quantity. As you can see, that is a logarithmic. And from our mathematics knowledge, we know that the argument in the logarithmics would be dimensionless. So at the end, it has to be a dimensionless quantity. So that is why when you write logarithmic or exponential quantities, you have to ensure that these arguments are dimensionless. That is also a counter check. Okay. So this describes the rate at which the particle moves with respect to a chosen reference frame situated on the trajectory of the motion. And earlier we defined your y as tan hyperbolic inverse of beta. This was from the definition. And then exploiting the properties of tan hyperbolic function, I could write as half of log 1 plus beta divided by 1 minus beta. And in terms of the energy and momentum, so I could write half log E plus P divided by E minus P. Okay. And it is not, it is difficult, but not always possible to measure energy and momentum in experiments. You have already noticed from our earlier discussions of Sanjeev also. And energy measurement requires calorimetry or trackers with PID, so that I can take the mass and momentum is measured through the trackers. So that is a difficult game. That is the region that we introduced to pseudo rapidity, and in the definition of pseudo rapidity you will find it only depends upon the heat angle. Okay, so that angle or the position is easier to know. Okay, so the notion of positive and negative rapidity, as I mentioned, is a convention. Okay, when somebody says it is positive or negative, so that is a convention, like your x-axis right hand side and left hand side. And the rapidity has a logarithmic dependence on energy and momentum. The last slide you saw that. So that is the reason the magnitude of the rapidity is rather small. Okay, even for the most energetic particle, even if we are in the high relativistic domain, so your rapidity absolute number for a particle is also very less, and the range of the rapidity in principle following the formula could be minus infinite to plus infinite. So now in the collision geometry, you have seen the rapidity variable makes annular rings on the detector geometry or the plane, and higher values are towards the beam pipe, so making it plus infinite or minus infinite. And once you go towards perpendicular to the beam, so slowly that value changes. Both rapidity y and the azimuthal angle phi will span the whole detector plane, which is our phase space. And rapidity formulation simply and naturally incorporates the Lorentz invariant Lorentz transformation properties of the velocity. So that I am going to show you. And the differences in rapidities are also Lorentz invariant. Okay. So yeah, so this is a beautiful, working problem. You can realize that the rapidity formulation is naturally incorporating the Lorentz transformation properties of the velocity. For example, let me take, we need to find the particle velocity v given. So one of the frame velocity is v0, which is 0.8 c, and the velocity of the particle in the moving frame is v prime. So that means you have a particle with velocity v prime, which is point c, sitting on a frame which is moving with respect to the laboratory at velocity 0.8 c. So now our problem is, let's find out the laboratory velocity, which is essentially a sequential or sequential Lorentz transformation. And if I remind you one of my earlier slides, my velocity can be written as v prime plus v0 divided by 1 plus this nonlinear. My nonlinear formula velocity I showed you earlier. Plug in these values and you will find 0.945 c is my velocity with respect to the laboratory frame. So using the rapidity formulation, if I go from velocity to rapidity, you will find my y0, okay, the frame velocity. If I plug in, so this is actually the rapidity of the frame, okay. And you can see, it is comparing with velocity of light so high, and rapidity, because of logarithmic dependence, it is now very less. Okay, so that gives a different freedom to us. Okay, so y0 is the rapidity of the frame, so which is 1.098, and similarly y prime rapidity can be calculated. The particle rapidity in the moving frame is 0.693. So just plugging in the velocity numbers, and I use the rapidity transformation formula, which is y is equal to y prime plus y0, and I'm getting 1.791. And then I use the formula for beta and I recalculate using this one. I am getting 0.945. And this 0.945 was the beta, was the velocity calculated here. Okay. So that means your nonlinear velocity transformation, whatever value that gives for a sequential Lorentz transformation, velocity, your rapidity is also giving the same thing, but rather it is just an addition, preserving your spectral shape. And this gives me a better freedom. And this also indirectly tells me or directly tells me that rapidity formulation is a relativistic realization of Lorentz transformation properties of velocity. Okay, so I find this is a beautiful formula. And whatever I discussed about different properties of rapidity and pseudo rapidity, so you can find this is the rapidity distribution, this is pseudo rapidity, and pseudo rapidity, that is a mid rapidity dip. So this is coming because of the mass dependent suppression, which I will show you the formula. And important point is the range of the rapidity, as I showed you, that changes with higher and higher energies. And since it is the total charge particle production in the collision, you will find more central collisions will produce more number of particles, and more is the energy of the collision that will also produce more number of particles. That is also reflected here. So if you see from AMPT 19.6 GB low energy to 200 GB high energy, if I go on, so I produce more and more number of particles. So high energies and higher number of particles participants in the collision will also give rise to more number of final state particles. So these things we are learning from these different curves, plots, and you can also find here. So if you go for top central collision, the centrality is defined to you in other classes. Okay, so the top central collisions will produce more number of dn charge by d eta, more number of particles. Okay. So then let me introduce pseudo rapidity quickly, and I start with your rapidity definition, and at very high energies your P is much higher than M. So this can be rewritten in terms of ignoring my P, E can be written as P, and then your Pz is P cos theta. This after I do this simplification, so you will find that I land up with the beautiful formula of minus log tan theta by 2, and I say that it is my eta, the pseudo rapidity. Okay, so eta is called the pseudo rapidity, and mostly that is used in collider experiments, because as you can see from the formula, a particular identification in terms of energy measurement or the momentum measurement is not necessary. Just heat position can give you eta. So that is one of the reasons that I did not know the particle identification, and this gives us indirect or better handle over rapidity. Okay, so at very high energies it can be shown that your y was like eta, which is minus log tan theta by 2. And in terms of particle momentum also you can show the eta expression. So this I showed you earlier. Let me skip this slide. And if you change from ypt to eta pt, essentially changing from rapidity to pseudo rapidity, so eta can be written in terms, just rearrange this formula, you will find e to the power eta is this and e to the power minus eta is this. So if you add both these expressions, you will find your P is equal to Pt cos hyperbolic eta, and if you subtract, you will find your Pz is Pt sine hyperbolic eta. So with these things, I am slowly changing from Pz to Pt and eta. So using these expressions, I will find my y can be written in terms of eta and Pt. So you reorganize the things and you will find my eta in terms of your total number of particles or differential number of particles dn as a function of pseudo rapidity, and Pt is there. You can integrate out Pt also, and on the other side you have y. So this is the conversion formula using conversion formula from pseudo rapidity to rapidity and vice versa. So as you can see, if your particle is massless, for example photon, so this term will be 1, the whole term will be 1, so this is 0 and the whole term will be 1. So there will be no distinction between pseudo rapidity and rapidity for massless particles. Okay, for massive particles there will be a massless mass related suppression at mid rapidity. Okay, so at y going to 0, so this term will be creating a depression in the formula, in the spectra for dn by d eta. So that is called mass dependent suppression. I think I showed you, otherwise I can show you my plot somewhere. Okay, these are some detailed discussions. I think I can skip those things. Those are more involved physics kind of discussion, how this Jacobian is changing from with different collision energy and all that. But I guess because of time, unfortunately, I have to skip few things, and how that is related to the emission of emission velocity of the particles, how that relates to eta and y. So lots of discussions I had put it, but unfortunately time is less. Yeah, so I can either stop here. Unfortunately, the only leftover stop I wanted is invariant yield and luminosity. So these two things are left over for me to discuss, but I think I have taken almost 1 hour plus time. So Siddharth, I think for any interested people, I can have another session sometime, or if they have any queries, they can get back to me. What I am leaving behind, not discussing because of time, is invariant yield, how luminosity is coming as a natural consequence, and the dimensional crisis of what we measure and how we transform to the cross section where luminosity should play a role, and the luminosity in fixed target versus collider. So this is what I am missing from the discussion. So since it is already a marathon run, I think if you like, I can stop here. Otherwise, it will be another 20 minutes.
Yeah, so Raghubhai, whatever is left over are also very, very important. But
yeah,
within this time constant, maybe we stop here and we can follow it up through emails or through maybe in some other forum. We can invite you and you can in any forum, actually, because we are mostly internal. So in Alice India meeting or somewhere, in some other forum we can.
Yeah, actually, last time what we did is we had 5 classes, and I was prepared with so many things for 5 classes, and exactly 5 classes I would have finished, because as you can see, from invariant yield to slowly I go to kinetic phase out properties and chemical phase out properties. Then I migrate to luminosity, and with a luminosity and event statistics example, I finish it. So that was my plan.
But if you can share at least these slides which are left over, because the rest anyway, it is there in the recording part. So that would be, I think that would be
no problem.
More useful. Okay.
Yeah, no problem, because last year school also my slides are there in the web page. So this can be shared.
These slides are there already, or
yes. Yeah, with no changes. In fact, with more material, last year's slide you can actually refer to.
Okay, then fine. So then anyone can follow it up and then can be discussed.
Right. So I request all of the students, please excuse me because of the limited time and my plan of 4 lectures, 5 lectures last year and a reduction to 4 lectures this year. The important part is not discussed. What I planned, you can see in my slides, and a superset of this is essentially there in the last year's school page. So have a look and get back to me. I am always I believe I'm a little student friendly. So except my own students who may complain like this month. So we'll discuss anytime. Yeah.
Okay. Thank you so much, Raghu bhai.